In this video, I would like to present two ideas from a book I recently read. These are the notions of sampling and exchangeability. However, since the book is rather technical, I cannot really recommend reading it. Along the way, we will see more general notions around network analysis, in particular some graph metrics and some random graph models. Let us start with a few definitions. Informally, a graph is a set of vertices and edges between those vertices. But there are many variants. The edges can be directed or not. We can allow multiple edges or not. We can allow loops or not. We will stick to the simplest of those variants, undirected with no loops and no multiple edges. Here is the formal definition. A graph is a set V whose elements we will call vertices and a set E of unordered pairs of vertices whose elements we will call edges. That representation as sets is not always the most programmer-friendly one. Alternatively, we can represent a graph as an adjacency matrix, a binary matrix with one row per vertex and also one column per vertex, with ones whenever two vertices are connected by an edge. There is one last problem, however, a more insidious one. The word graph is used for three different notions. First, a graph can be a set of vertices and edges, as we have just defined. That's what graph theory studies. Second, a graph can be a random graph, i.e. a random variable whose values are graphs. We can then do statistics on this random variable and compute, for instance, the average number of edges, or look at the distribution of the degrees of the nodes. Often, the set of vertices will be constant. Third, a graph can be a sequence of random graphs, whose number of vertices tends to infinity. We can then study, for instance, the asymptotic properties of those sequences. It's not always clear which of those three definitions is used. If a statement does not make sense, the author may be using a notion different from the one you assume. Graphs are everywhere. I will not detail those examples, but just list them. You can Google them yourself if you want more. There are physical networks, such as the road network, the electricity grid, oil pipelines, and the telecommunication networks. There are social networks, keeping track of who knows whom or who collaborates with whom. There are networks in biology, modeling interactions between genes or molecules, or between species, the food web. The Internet is yet another network, with web pages linking one another. Given a graph, we can compute a few numeric quantities that summarize some properties of this graph. We can call them graph metrics or graph features. I will not give precise definitions, we do not really need them, but just list the most important of those features. The first ones are straightforward. The number of vertices, which measures how big the graph is, and the number of edges, which measures how dense it is. For each node, we can compute its degree, the number of edges connected to it. For the whole graph, we can look at the degree distribution, how many nodes of each degree there are. For each pair of nodes, we can compute the shortest path distance between them. For the whole graph, we can look at the distribution of those path lengths. We can also count the number of triangles in the graph, the so-called clustering coefficient. Finally, we can measure in different ways how central a node is. There are several such notions of node centrality, and as before, for the whole graph, we can look at the distribution of those centralities. For real-world networks, some of those quantities exhibit stylized facts. Let us list a few of them. Real-world networks are scale-free, which means that their degree distribution is a power law. Most nodes have a small degree, but a few nodes have a very large degree. Here is a simulated graph and its degree distribution. Most nodes have degree between 1 and 5 and there are no outliers. In contrast, this network, with approximately the same number of edges, has a few nodes with a very high degree. In real-world networks, distances tend to be short. This network is a grid. The path from one end to the other is rather long. Real-world networks are closer to this one, which is the same with a few random shortcuts added. Real-world networks, in particular social networks, tend to have a lot of triangles. Friends of friends tend to be friends. The examples we have seen so far had very few triangles. From that point of view, this one is more realistic. Real-world networks tend to have some structure, often with communities more or less delineated, with more edges inside than with the outside. We now come to the first point of the book, sampling. When we examine a real-world network, we rarely have access to the whole network, but just to a sample of it. This is not uncommon in statistics. We often only have a sample from a population, and we need to infer properties for the population from those of the sample. While those properties are close, they need not match exactly. You are undoubtedly familiar with the difference between the sample variance and the population variance. Things are much worse with graphs. The sampled graphs often look nothing like the whole graph, and the relation between the two vary widely with the sampling procedure. Let us review some of those sampling procedures. In vertex sampling, we pick nodes at random and look at the induced subgraph. As you can see, it is much less connected than the initial graph and can even have many isolated nodes. In edge sampling, we pick edges at random and look at the corresponding subgraph. This is what we get, for instance, when we intercept communications. The problems are similar. The graph looks much less connected, much less dense than it actually is. Snowball sampling starts with a node, adds its neighbors, then the neighbor's neighbors, and so on for a few steps. This gives a good idea of what the graph looks like near the seed node, but nodes on the boundary look much less connected than they actually are. To have a better idea of what the graph looks like in other regions, we can apply the same idea to several seed nodes. Path sampling picks two nodes at random, retrieves the shortest path between them, and starts again with another pair. This is what you get when you look at the internet with the traceroute Unix command, for instance. I will not mention hyper-edge sampling here. To study the properties of graphs, we can first devise random graph models and fine-tune the parameters of those models to reproduce the properties of real-world graphs. Let us review some of those models. The simplest random graph model is the Erdös-Rényi graph. The set of vertices is fixed, and each edge is present with probability p. The edges are independent. We saw this example earlier. Its degree distribution was not realistic. It lacks high-degree nodes. To remedy this, the Barabasi-Albert preferential attachment graph adds the nodes one by one and links new nodes to existing ones with a probability proportional to their degree, so that high-degree nodes see their degree increase faster. It is closer to what we expect from real-world graphs, but there are too few triangles. The Watts-Strogatz model tries to remedy this in a rather simple way. It starts with a graph with lots of triangles and adds or rewires a few edges at random. This is a graph with lots of triangles, and here it is with a few more edges. The stochastic block model is a generalization of the Erdös-Rényi model. In the Erdös-Rényi model, the presence or absence of an edge can be seen as a Bernoulli random variable, always with the same probability p. For the stochastic block model, the nodes are partitioned into several communities, and there's a different probability for within community and between communities edges. The graphome is yet another generalization of the Erdös-Rényi model. The Bernoulli probabilities are given by a function phi defined on the square, which can be seen as a continuous analog of the matrix we just used to present the stochastic block model. If we want a graph with n vertices, we just take n points uniformly at random in the interval 0, 1 and use phi to build the matrix of Bernoulli parameters. The graphome can be used as a random graph or as a sequence of random graphs with an increasing number of vertices. In this case, we may want to adjust the probabilities to have the desired edge density, lest there be too many edges. The exponential random graph model allows us to specify which graph properties we expect. It assumes the log probability of a graph is a linear combination of graph features, and you are free to choose the features you want. We now come to the other idea of the book, the most technical one, that of exchangeability. Some of you may have seen that notion in the context of the definity theorem. An exchangeable sequence is a sequence of random variables whose joint distribution is left unchanged by finite permutations. For instance, a sequence of IID random variables is exchangeable. But exchangeable sequences are slightly more general than that. We can wonder how far they are from being IID. This is what the definity theorem tells us. They are not very far. They are mixtures of IID variables. This can be written more formally, but it may not be that insightful. The notion of exchangeability can be generalized to graphs. A random graph model is vertex exchangeable if its distribution is invariant under permutation of the vertices. Unsurprisingly, there's a graph analog of the definity theorem. A vertex exchangeable random graph model is a continuous mixture of graphons. Since graphons are just generalized Erdös-Rényi models, they are not very expressive. The notion of exchangeability can be generalized to relative exchangeability by considering only some permutations of the vertices, as in the stochastic block model, or to edge exchangeability. In all cases, there is a definity theorem. This is a rather negative result. Most random graph models are exchangeable in some sense and therefore mixtures of simplistic models. They are unlikely to be powerful enough to accurately model real-world graphs. In conclusion, this video was supposed to be a book review but turned out to be more a presentation of graph sampling procedures and random graph models. The book conveyed two ideas. First, we never observe the graph we want to study but only a sample of it. The properties of the sample and the original graph can be very different, and the relation between the two heavily depends on the sampling procedure used. Second, most graph models are exchangeable, but exchangeable models are continuous mixtures of slight generalizations of the Erdös-Rényi model. They are not expressive enough. On our way, we encountered a few interesting ideas. We saw that the word graph was used to refer to three different notions: either an actual graph, a set of vertices and nodes, or a random graph, i.e. a graph-valued random variable, or a sequence of random graphs. We have reviewed the stylized facts of real-world graphs. They tend to be scale-free, i.e. to have a parallel degree distribution. Their typical distance tends to be small. They tend to have lots of triangles, and they often have a community structure. We have listed but not detailed a few graph metrics or features: the edge density, the degree distribution, the distance distribution, the number of triangles, and measures of centrality. We have introduced some commonly used graph models, such as the Erdös-Rényi model, in which edges are independent with the same probability, the Barabasi-Albert preferential attachment model, in which nodes are added one by one and connected to existing nodes with a probability proportional to their degree, the Watts-Strogatz model, which starts with a grid full of triangles and adds a few random edges, the exponential random graph model, in which the log probability of a graph is a linear combination of graph features, the stochastic block model, a variant of the Erdös-Rényi model with different probabilities to reveal a community structure, and the graphon, an infinite generalization of the Erdös-Rényi model.